Today we're going to talk about the beginnings of Chapter 7, which is exponential growth and decay. And just so you know what the graphs look like, the graph on the left is a growth graph. The concept behind growth in an exponential format is that as we move across our domain from left to right, or from negative infinity, which is over here, to positive infinity, which is eventually over there, our y values continue to increase, right? They continue to grow. And on the other side, the decay would be that same thing. As you move across from left to right, our y values would be declining or decaying. And the concept behind exponential is that the growth or the decay between each step is a percentage, and it's a consistent percentage. That's what makes exponential kind of special. There's a format that we use for exponential. It's a pretty fancy looking formula. Well, it looks like this one. I wrote on top there, exponential growth or decay of stuff. The first variable is just the name of the function. So that whole thing is going to be the amount of stuff that you have, whatever the stuff is, the amount of stuff you have after t time periods, right? However many time periods, whether that's in minutes or seconds or in years. The second a, which they just happen to be the same letter, but lowercase a, the second a stands for the initial amount. So if we're talking about a bank investment, that's going to be how much money you put in right in the beginning. If we're talking about population, it's whatever the population is in the beginning of our episode. And the final value, t, you could probably guess, stands for time, or the number of time periods. This doesn't always have to be minutes or seconds or hours or years. It can actually be some other kind of time interval. So that'll depend upon the question. Let's look at a couple questions to see how this is used and what it looks like. So let's look at a money example, right? This is pretty common. Invest $2,000 in a savings account last year, 2020. The account pays 4% annual interest. How much money will be in the account 10 years later? Now, the concept behind this is that every year you're getting 4% added back on to your initial amount. So that concept is that each year you add a little bit more on than what you added the previous year. That change in percentage each time is what makes it exponential. So let's take a look at this investment question. We want to know how much money will be in the account after 10 years. So I'm going to do A of t, right? We want to know how many dollars are going to be in there after 10 years. We're going to go ahead and say the initial investment is $2,000. So 2,000 goes in the low A spot. I have 1 plus, now my growth rate is 4%. Now 4% is the same as 0.04. And the t value is going to be the number of time intervals. And in this case, the number of time intervals is 10 years. So I'm going to take the t out and replace it with the 10. And now this is really just a calculator task. I'm going to type in 2,000 times 1.04, and then I'm going to raise it to the 10th power. Now, regular calculators are really powerful for this. I'll use my iPad calculator. So I'll start with parentheses, 2,000. And the way my calculator works, I have to hit a times in between. So times, and then the next one would be the 1 plus my growth rate of 0.04, or you could have just typed 1.04, and then I'm going to raise it to the 10th power because we have 10 years. And when I press equals, I have the amount of money that will be in the account after 10 years, $2,960.49. The second style of question usually relates to growing something that is exponential, but one that we have data, not percentages. So this one says, what if we have data on 2 consecutive data points? We assume the data is exponential. Can we create an exponential model in order to make predictions? So we're going to go ahead and make some if statements here, right? Giant ifs. If we have the data, if it's consecutive, if we can assume, there's lots of ifs, but textbooks love this kind of stuff. So let's imagine that we've counted up the number of dogs in Texas. This is an absurd number, but let's just pretend. So in 2019, we counted up every dog in the state of Texas, and it was 150. If it makes you feel better, call it 150,000 or 150 million. We're just going to go with 150 to keep our numbers easy. Now, the following year, we're going to say it's 2020, and the number of dogs in Texas has grown to 180 or 180,000 and so on. So what I need to do is I need to come up with a percentage of growth. This is exactly the same thing as percent of change. And percent of change is a very simple formula. It's the new information minus the old information divided by the old information. And then if you want to make it a percentage, which we do not, you'd multiply it by 100. So the newest information is the 180 because it's the one from the most current year. The old information is the 150, and we divide it by the original or the old information 150. So we'll do a 180 minus 150 divided by 150, and I get myself a 0.2. That's my growth rate. And that 0.2 is a positive number, so that means we're growing. So that 0.2 is going to go here. All right, so now let's see what else we have. So now I'm going to take this, I'm going to say we have a sub t is a of 1 plus 0.2 of x. And I'm going to change something out here because it's going to help me. I'm going to go ahead and say y equals, because we can do that with function notation. I'm going to take a particular piece of information, but I'm going to change colors, and I'm going to say instead of 2019, I'm going to pretend we're at year 0, and I'm going to call this x equals 0, and I'm going to say y equals 150. It's going to be how I would organize a table. So I'm going to swap out my 0 and my 150 in the x and the y spot. So the y is going to become a 150. I'll stay with pink just so it shows some consistency, and my x is going to be 0. All right, so let's go back to black. So I have 150 equals a times, well, this is going to be 1.2, but anything to the 0 power is going to be 1, so this is 150 equals a times 1, so 150 equals a. So now I have some information, and I can probably write my exponential model. So y equals, or a sub t is, let's see, 150, 1.2 to the x. And this is something that I can graph. Right now I have an exponential model. So what would it be? Back to pink so it makes some sense. If this was 1 year later, this would have been x equals 1. This is 5 more years on top of that, so 1 plus 5 is 6. So if I wanted to calculate the number of dogs I'm going to predict in Texas in 2025, I'm going to put a 6 into x. I'm definitely going to use a calculator. So here goes the 6. And once again, into my calculator, I'm going to remember these numbers. 150, 1.2 raised to the 6th power. And I have, this is an astoundingly high number, 440, let's round it up to 448 dogs. So all of a sudden that small growth ends up being 448 dogs.